So continuing question 4, we're about to do part C. So we just need to recall the result we had from part B, which was that the Laplace transform of this function f, and I remember what it was 1 minus 2 e to the minus 2s plus e to the minus 4s times over s squared. Wasn't that it? Is that our Laplace transform of function b?
Yes.
Yeah. So part C, we need to solve the ODE. We solve this ODE subject to the 0 initial conditions on the function and its derivative. Those are the simplest kind of initial conditions to have because they remove some of the constants from the transformed equation. Yeah. So you should, in answering these kind of questions, you should just, give a good demonstration of the method, supply the justification where it's needed to indicate your understanding of the material. Okay, so the usual advice. Okay? So we begin by transforming the equation, transforming the whole equation. So we say the Laplace transform of the left-hand side, which by linearity is the Laplace transform of the individual parts. So this is going to be equal to 27 times the Laplace transform of f of t. So we're using linearity there. Linearity for transforming the left side and right-hand side. So this is going to imply that, and now we want to use the transform of derivatives property. So the transform of a second derivative. And we're also going to write, what do we write? Y bar for the Laplace transform of y. So rather than keep writing this expression, Laplace transform of y, just give a more compact notation, y bar. So then this thing here is going to be s squared times y bar minus s times y of 0 minus y dot of 0. So that's the transform of derivatives property for a second derivative. That's read from the table. And then we got 9 times y bar equals this thing up here. 27 times this combination of exponentials. Over s squared. So what do we indicate? They're writing this and using the transform of derivatives property. Transform of derivatives property from the table. And then we can put in the initial conditions. That's going to simplify it a bit more by cutting out those two. Now, rather than keep rewriting and rewriting, let's do a couple of things at the same time. So bringing in the initial conditions will rub out those two terms. And then the left-hand side, then I can factorize as s squared plus 9 multiplied by y bar Okay, but then I'll divide both sides by s squared plus 9 to solve the transformed equation. So we've got 27 over s squared plus 9 times s squared, and this is all multiplied by this bracket here, 1 minus 2 e to the minus 2s plus e to the minus 4s. So what did we do there? We imposed the initial conditions and we solved for y bar. Okay, just some comments to explain to the reader what's happening. Okay, so we rub out those two because they're both 0, and factorize the left-hand side, s squared plus 9 times y bar, and then divide both sides by that s squared plus 9. Now, so we're kind of halfway. We've solved the transform problem. In principle, we just need to take the inverse transform. Okay? You take the inverse transform of y bar, you get y of t, the solution to the differential equation, and it's going to be equal to the inverse transform of this expression on the right-hand side. Okay? But how do we take that inverse transform with the information that we've got? Okay? The information you will have to hand in the exam, of course, is the table of Laplace transforms. Clearly, you won't find anything that fits that pattern exactly on the table, nice and simply, so that you can just read off the answer. But the structure here is you've got these various exponentials, okay, the trivial exponential 1, and then these other exponentials. You've got those various exponentials multiplied by this function of s. So what's going on there is we've got many instances of this expression here. Some exponential multiplied by a function of s, multiplied by a certain Laplace transform, that 27 over s squared plus 9 times s squared. Okay. And you've got varying values of a for those three. For a equals 0, it's the 1, a equals minus 2, e to the minus 2s, and a equals minus 4. So we got 3 instances of this result. Okay, so we're going to read off the inverse transform as this expression here. This gives you the reappearance of the Heaviside step function, and then this shifted inverse transform f. Okay, so so that's the overall mode of attack we're going to use here. So this is our f bar of s, and these are our different exponential factors. Okay. So that f bar of s is that big fraction, 27 over those s's, and then we got various exponentials. Okay? So we will apply the result, the Laplace transform of f t minus a times the Heaviside of t minus a equals e to the minus as f bar of s. So we'll apply it 3 times here. 3 times here, where f bar of s is this function here. But in order to apply that, we're going to have to get, we're going to have to obtain the f, is the inverse transform of f bar. Okay. So that's something we have to separately do. So we park that expression for y bar there for the moment, and we take the inverse transform of this f bar. We need to obtain f of t. Need to know what f of t is because we're going to have to apply it several times here to take the inverse transform of that. For this, we need partial fraction expansion. Okay. So we need a partial fraction expansion of f bar of s. Now that could, for a function like this, it potentially could be, yeah, a little bit complicated, because you've got these. This is the factorization of the denominator. It's already factorized for you. You've got an irreducible quadratic factor here, s squared plus 9. So its numerator has to be an a plus bs. And then the other factor is this multiple factor s squared. So you need something over s and something over s squared. Okay. However, so in general, if you just had a typical numerator there, you'd have to consider that you might have all of these parts here. You have to collapse it again, look at the behavior of the numerator, compare the coefficients of s, and so on. But in this case, the numerator is just a single constant. So we can fairly reliably just shortcut the process of getting the partial fraction expansion. Because, yeah, like which of these, see, if you did have the full-blooded thing here and collapse the whole thing into a single fraction, which bit here generates a constant in the numerator? Which bit would end up being a constant in the numerator? Sorry? Yeah, the d. The d would end up being a constant, because when you collapse the whole thing to a single fraction over the common denominator there, the d would end up getting multiplied by s squared plus 9. So the d would hit the 9, and you get a 9d, a constant. All the other constants, the a, the b, the s, and the c, they will all end up multiplying s, or a higher power of s. So the only way to obtain the constant 27 is that if d does the job. So d has to be equal to 3. Okay? So we need d equals 3, since it generates the constant in the numerator. But of course, if you decide that d is 3, you also get a 3s squared in the numerator. But of course, there ain't any s squareds in the numerator, so we have to cancel that s squared. So which bit gives s squareds in the numerator? A. Because when you collapse that thing together to that single fraction, the a ends up getting multiplied by s squared. So the a generates more s squareds. So we're getting 3s squared, but we don't want any, so we better make the a to be minus 3. And with a equals minus 3, we get the desired expansion. So it is possible to shortcut the process there. So f bar of s is minus 3 over s squared plus 9 plus 3 over s squared. Okay. But if you went through the full rigmarole, you come out with those solutions in the end anyway. That b and c have to be 0, and a and d have to be minus 3 and 3. Yeah. So, we want the inverse transform of this f bar. We want the f of t. So using the table and linearity, we can say that f of t, which is the inverse transform of f bar of s. So it's the inverse transform of these two. These you can find on the table, or you can find multiples of them on the table. I should take the 3's outside there, but it's minus 3, so 1 over s squared plus something, what's that? Oh no, I need omega over s squared plus omega squared, so that's a sine of omega t, so sine of 3t. There's a minus sign, so it's minus the sine of 3t, is that right? And the 3 over s squared, that's plus 3t. Okay, so that's the f of t quantity. Is that okay? Any queries about it? So that f of t quantity, where we'd said how we wanted to use it, it's going to appear here, evaluated at some shifted argument, t minus a, for various values of a, for these 3 values of a equals 0, a equals minus 2, and a equals minus 4. So now we can get y of t as y of t is the inverse transform of y bar. Using the property star. So I'll just go back and label this property here with an asterisk. This one. The one involving the heavy side and the exponential. So using that property star and linearity, so it's f of t minus 0 times h of t minus 0 and minus 2 times f of t minus 2 times h of t minus 2 plus f of t minus 4, h of t minus 4. Yeah?